Hello and welcome to Module 4, Modeling and Simulation. Here we will discuss Introduction to Simulation Modeling. Start off with a very definition of simulation and an overview of what simulation is. Simulation is a broad term, but it typically refers to using computers to mimic the performance of an actual real system. This is a pretty powerful tool because it allows systems to be analyzed and adjusted without completing them or making adjustments to those actual systems. This applies to many fields and industries and is considered a very powerful tool. In this course, we will cover the general system concepts, but for the actual modeling simulation, we will use Arena software. Arena is a software program and is one of the most widely used simulation software programs available today. It's created by Rockwell Collins and has been used very effectively by a multitude of businesses across very different industries. At the same time, there are other simulation programs available, and any of them would follow very similar concepts. Generally speaking, simulation involves imitation of a system, typically by a computer. It will not produce exact results, however, it will give directional information given the framework provided. Like many other tools, it can be very effective, but is only as effective as the quality of information it receives put into it. Simulation is a core competency within the field of systems engineering. It's universally appreciated for its ability to test and evaluate complicated systems without incurring the high cost to do so. So as we defined previously, a system can be a facility or a process. For modeling purposes, it can be existing or planned. And in many cases, it is planned or theoretical because it's good to evaluate those before you go to the expense of constructing it. Many examples possible. Manufacturing facilities, bank operations, airport operations, transportation, logistics and distribution, hospitals, computer networks, freeway systems, business processes such as an insurance office, criminal justice system, chemical plant, fast food markets, supermarkets, theme parks, emergency response systems, shipping ports, military combat. All of those are considered systems. All of them have inputs and all of them have outputs. Any one of those conditions above and a multitude of others could benefit from using simulation modeling to evaluate and understand the implications across the whole system. So in a study system, there's measure, improve, design, and control. So maybe just play with the actual system is one option. It's an advantage as you could unquestionably be looking at the right thing. However, it's oftentimes impossible or very difficult to do so. The system may not exist, or perhaps it'd be disruptive or expensive or just not particularly feasible. So in many cases like this, the actual complete system just can't be modeled. Perhaps it hasn't been constructed yet, or you want to just evaluate a potential change. It's also possible you may want to evaluate it without regards to external factors that you can't control in the real world. The ability to do these things is a primary advantage of simulation. The primary use for simulation is to develop an analytical model. This will give you tangible answers to a system given a multitude of inputs and the potential of impacting overall system behavior. The analytical model will create a model that has mathematical methods in obtaining exact information on the questions of interest, and often can give you a very exact answer to a problem of approximation. So for example, you might go and say, how should we go and define this? And you might be able to get a very concrete mathematical answer as a result. Other main uses of simulation is that they can be used for a variety of what-if questions. So they could be used to predict the effects of changes to an existing system, or for predicting the performance of new systems during their design phase. Other uses for simulation include verifying analytic solutions, using animation to show how a system in simulation operation so that it can be visualized, and to train workers without the cost and disruption of on-the-job learning. Consider the example of road layouts and traffic patterns within a large city. Changes will be both time-consuming and difficult to implement. Simulation could account for the patterns and the traffic behaviors, allowing for evaluation of many different options. To that end, an engineer could evaluate many alternatives, including making the street one-way, adding an extra lane, or changing a traffic light, and could do all those things without impacting actual traffic. So the model is a set of assumptions about how the system works. It will include inputs and their associated behavior. In creating the model, it's very important to get good quality inputs. If they are not correct or not valid, they will often yield misleading results. Creating the model is certainly easier than building the actual system, but it can be a very laborious task. The system engineer must consider all the factors with the potential of influencing the results. While this is a time-intensive process, it is worth the investment for large systems given the ability to identify and react to issues prior to implementation. A common question in modeling is, how detailed should you take the model? For the purposes of this course, the models will be very simple. However, in the real world, models would be increasingly complex. As a general rule, the more complicated the system, the more important it is to develop a truly detailed model. There are two types of models. Physical models, or iconic models, are typically representative of physical or practical systems. Examples would be the material handling within a delivery or manufacturing setting, fast food restaurants, or flight simulators. All those are very tangible and physical systems. Logical models, on the other hand, are less tangible, but not any less important. They are typically more applicable for systems that aren't physical in nature, maybe more conceptual, or maybe more virtual. Examples would be computer, hardware, or software operations. Other areas of application include manufacturing. You can use them for scheduling or inventory flow. Military, logistics, transportation, and distribution. You could use this for designing a specific transportation facility, including freeways, subways, or airports. You could use these for business processes, staffing, and personal service operations, such as a bank or fast food restaurant, theme park, or post office. Healthcare, such as emergency rooms or operating rooms. Telecommunications. Public policy or response time, such as emergencies or public services. All these are examples of potential applications, and there are many others to consider. So there are also times when simulation is not appropriate. Simulation should not be used when the problem can be solved using common sense or can be solved analytically. It also should not be used if it's easier to perform direct experiments. In some cases also, the cost of developing, testing, and executing the simulation exceeds the potential savings. If the simulation is simple enough that the answers are fairly clear, there really is no point to develop a model to evaluate it. Also, since one of the main benefits of simulation is risk mitigation, this risk may not be as critical in some applications such as some of the ones we described above. Just like any other tool, it needs to be used in the appropriate setting, and common sense needs to rule out. Advantages of simulation include repeatability, in that you can repeat experiments exactly. And one nice thing about this is you can go and rerun a simulation and making minor adjustments and truly understand the impact of adjustments. They could be very subtle or they could have a very profound impact. And simulation modeling can do that and give you that answer. It's typically easier to apply than some of the analytical methods. It's easier to generate. While time-consuming to set up, it can be oftentimes easier to understand the system behavior with a large number of variables at play than to try to create something manually. Generally speaking, it requires fewer simplifying assumptions than do analytical methods. And this is because software has been developed and refined over the years and has been customized to be very versatile to a multitude of different scenarios. You can typically generate more data faster than in a real-life system. Once the model is developed, these results can be evaluated very quickly. This is especially helpful when brainstorming modifications to a potential system, because you can get an answer very swiftly to any potential question that comes up. This can be helpful by throwing out an idea, evaluating it, and continuing to move on without disrupting the continued line of thought in the process. Disadvantages of simulation in that, first of all, it is very time-consuming. In model building and documenting and validating and verifying, it takes quite a bit of time. Even just going and collecting all the data can be very time-consuming. It also could be used inappropriate. If you have improper data inputs or outputs analysis, you could have short-sighted information, and that could give you bad outputs. It also could be used when other methods, such as analytical methods, would be more appropriate. Just like anything else, it is a tool and should be used in appropriate situations, but it shouldn't be the only tool leveraged for every considerable situation. In studying logical models, if the model is simple enough, you can use traditional mathematical analysis. You can get exact results and lots of insight into the model. Other things such as queuing theory, differential equations, and linear programming are other tools that may be valuable. However, in complicated systems, you can very seldom represented by a simple analytical model. The danger of oversimplifying assumptions is that you oftentimes lose the true value and some of those impacts of the variability within the system. At the same time, complex systems can seldom be validly represented by a simple analytical model. In those cases, there's oftentimes oversimplification, which sound easy and make it much easier to set up. However, you lose a lot of the validity and a lot of the value in truly understanding the impacts of all the different interconnections. There's also what we call, in this case here, the type 3 error. If you're familiar with the type 1 and type 2 error, a type 1 error would be identifying something as a defective or defect when it is truly not. So that's a scrap risk. Type 2 error is considering failing to identify a defect when in fact there was one, and that's a consumer or defect risk. In this case here, we kind of talk about the type 3 error, which would be working on the wrong issues. This would result in unnecessary resource and time allocations to spin your wheels and not making the system any better in the process. So computer simulation, methods for studying a wide variety of models of systems. So you can numerically evaluate on a computer and use software to imitate systems operations characteristics over time. Many people not trained on simulation will attempt to develop it on a computer analytically. This can work, but it isn't as efficient or as reliable as using software specifically designed for the system. It also becomes increasingly less likely to work the larger and more complicated the system involved. Computer simulation can be used to study simple models, but it should not be used if analytical solution is available. And the real power of simulation truly comes in complicated models. Again, simulation is the most powerful in these large complicated systems. Smaller systems tend to have less variables to consider and less overall risk, so they can be evaluated with simpler terms, not requiring the construction of a full model. So let's consider an example of a simple processing system. Let's say in this case here, blank parts arrive to a drilling center. The blank parts, of course, being the inputs. The parts are then processed by a single drill press and then leave. The finished part would then be the output. The drill press would be the machine or the process throughout. When a part arrives, the drill press is idle, the processing can begin immediately. However, if the drill press is busy, it will have to wait in a queue. The components of the system, we first would start with the entities. An entity is the object of interest within the system. In our example here, the entities are the parts. These are the players that move around, change status, affect, and are affected by other entities. So dynamic objects can get created, move around, and leave. And sometimes they may even continue to circle throughout the system. They typically represent real things and can have different types of entities concurrently. Attributes is another component of that system. The characteristics or properties of all entities, they describe and/or differentiate entities. Essentially, the attributes describe how these entities will behave. For example, if the entities here are the parts, an attribute would be when they arrive and be ready for use. All these entities have the same attribute slots, but different values for the different entities. So they could have values for time of arrival, due date, priority, or color. The value of the attribute is tied to a specific entity, analogous to the local variables in computer programming. Continuing with the attributes, an attribute is like a categorical characteristic of an entity. So color, priority, or weight. It has to be categorical, cannot be continuous. You can think of it as an attribute as a placeholder, like a column label on a spreadsheet. Then each particular entity has an attribute like blue or high or 8 pounds or something about that entity. So an attribute value can be thought of as the row in the spreadsheet. Therefore, the contents of each cell in the spreadsheet represent the attribute value that relates to the attribute with the part. Let's talk about activities. An activity is a duration of time or specified length. Examples would include service time or inter-arrival time. In our instance here, with the drill press, the activity would be the processing time within that drill press. State variables are a collection of variables that contain all the information necessary to describe the system at any time. In our example again, the possible state variables could be the status of the drill press. It could be busy, idle, or down, or it could be the number of parts waiting. An event is an instantaneous occurrence that may change the state of the system. In our simple processing example, the event would be an arrival of a part or completion of the part by the drill press. Resources are what an entity competes for, such as people, equipment, or space. Just like any other application within systems engineering, project management, or similar disciplines, a resource has a very similar connotation. An entity will seize a resource, use it, and then release it. Think about a resource being assigned to an entity rather than an entity belonging to a particular resource. One resource can have several units of capacity, so one table might have multiple seats at a particular restaurant. You could have identical ticketing agents at an airline counter. The number of units in a resource can be changed during the simulation. In our example of the resource would be the drill press. Queues are places for entities to wait when they can't move on. Maybe because they have a resource that they are waiting on, or because they can't get to a particular end. Queues have names, and they are usually tied to a corresponding resource. Queues can have a finite capacity to model limited space. In this instance, we have to model what happens if an entity shows up to a queue that's already full. We are usually interested in the length of the queue and the average maximum waiting time in it. Queue behavior is customer actions while in queue waiting for service to begin. Understand that queue behavior may change based on how things occur within the system. For example, there might be balking, which is leaving the system when they see the line is too long. An example of this might be if you call customer service and you get told right away that the wait time will be 20 minutes and you decide you don't want to wait that long. You may hang up immediately based on the length of queue. If you were to call a different time and there was 2-minute wait, you might be willing to wait. You might be willing to wait and continue to stay in the process. Reneging would be leaving the system after being in line when they see that the line is moving too slowly. It could be a physical line, but again, with the call center example, perhaps they didn't tell you up front how long the wait was going to be, and after 10 or 15 minutes, you decided you didn't want to wait anymore. Then you go and hang up. Or jockeying, moving from one line to another if they think they have chosen a slow line. A good example of this would be the grocery store, when you find yourself in a line that's moving slowly, so you look around and find one that's shorter moving faster, and then you go and switch to that line. Each of these has to be accounted for in order for the system to truly reflect the actual behavior. Queue discipline also includes the logical ordering of customers in a queue. Queue discipline determines which customer will be chosen for the service when the service comes free. There are different types of queue disciplines to consider. You could consider FIFO, which stands for first in or first out, LIFO, which is last in, first out, SIRO, which is service in random order, SPT, shortest processing time, or PR, pre-specified. This would be service according to a priority. FIFO is typically the most common that I have experienced in the professional world, but any of these could be the case. In fact, some cases you might look and say, even though the first in might be the first out, we'd rather have the shortest processing time to reduce that bottleneck and get the queue down. You have to look at what your real-life simulation is going to be in order to truly understand the queuing discipline. Using computers to simulate, generally speaking, there's many different languages that they program simulation software in. You can use it in C, C++, Java, Fortran, whatever you choose. Typically, these are tedious, low-level, error-prone, and not particularly recommended. Of course, the advantage of hard coding this in is that it does promote flexibility. Support packages do exist for general-purpose languages, with subroutines for list processing, bookkeeping, time advance, etc., and those are widely modified and used. Spreadsheets can be fairly helpful, especially in static models. Potentially within dynamic models, but not very frequently, and if so, they would have to be very simple. Financial scenarios, distribution sampling, and SQC are some examples. You can also see more in Chapter 2, where it has examples of static and dynamic examples using spreadsheets. Some advantages of simulation include computing and cost ratios. It's been estimated that approximately 75% of computing power is used for various kinds of simulations. Oftentimes this includes dedicated machines, such as real-time shop floor control, to understand and manage systems ongoing. Advantages in software simulation include that they're far easier to use, they're no longer restricted to modeling constructs, and the statistical design and analysis capabilities have advanced significantly. The bad news is that they don't always get exact answers. You get approximations and estimates with simulation. It also can be true of other modern methods, and can bound errors by machine rounding. You also lose random output from stochastic simulations. So statistical design analysis of simulation experiments. There are two types of systems that we will examine here, discrete and continuous. A discrete example would be when a state variable changes only at a discrete or at a point of time. However, a continuous system would be when a state variable changes continuously over time. A discrete example might be when the state variable changes when a part arrives or begins processing at the particular drill press. Conversely, a continuous example might be an airplane moving through the air. In that case, the state variables, such as velocity and position, will change continuously with respect to time. Other types include static and dynamic. Does time have a role in the model? That determines whether you have a dynamic or static model. Static models will represent the system at a particular point in time, while dynamic models represent systems as they continue to change over time. So an example would be the simulation of our simple processing system from 8 a.m. to 5 p.m. Always consider the impact of time. Do inputs act differently based on when they occur? For example, a walk-in clinic might have heavier volume on Monday mornings than at any other time during the week. Health insurance consumers might often use medical services more late in the year because they have flex dollars to spend before they expire. Consider all these different things because all these will impact your system as you simulate. Deterministic versus stochastic. Is everything known or is there uncertainty? Deterministic models have no random variables and have a unique known set of inputs and result in a unique set of outputs. Stochastic models have one or more random variables as inputs and random inputs leading to random outputs. In the real world, most models are dynamic, discrete change, and stochastic. For the purpose of this class, we will provide an overview of the discrete event system simulation. However, the reality is that most actual systems are complicated and need the more advanced modeling. So where ARENA fits in, ARENA has a hierarchical structure that has multiple levels of modeling that you can mix with the different types of modeling. You can also start high and start with a simple model and then add in more information as you go. You can use ease of use advantage of simulators without sacrificing the model flexibility. Simulation models like ARENA have been used for a number of years and have advanced along with the computer technologies. In the early years, in the 50s and 60s, they were considered very specialized tool and were very expensive. They typically required very large computers and programmed in Fortran or older languages. Processing cost oftentimes was as high as $1,000 per hour. And again, 1950s $1,000 very different than today. Realize too that $1,000 per hour may sound like a lot, but it also underlines the value in how critical simulation modeling can be and understanding the system before you will go and implement it. In the 1970s and 80s, computers got much faster and the value of simulation became much higher. As the software improved, the languages still need to be learned, typed, and processed. They're often used in retrospective, like cleaning up disasters in auto and aerospace industries. So instead of going and fixing a problem before it occurred, it would find why is something happening and go to troubleshoot and fix it. In the recent years, it's gone even further to the microcomputer power, and software has expanded, and animation started to become included. They've also become widely accepted in greater levels of industries, not just the traditional manufacturing service types of things, but also healthcare business processes as well. They're still primarily in large firms, but they are still oftentimes part of specs. Usually they are considered a core element within systems engineering. In today's world, they're proliferating into much smaller firms and becoming more of a standard tool than ever before. They're also being used earlier in the design phase and being much more of an expected element as opposed to a nice to have. The graphics are getting better and the dashboards are getting even more advanced. The future is anybody's guess, but the expectation is that you'll see further integration with other applications and increased visualization and analysis. Expect to also see networking of sharing and data in real time and internet-enabled technology for model building and execution. Also expect to see more templates for specific industries and firms and better ability to reuse models and not have to make models from scratch. Even though much of the technology is advanced, the concept of building the model from the ground up is still functionally the same as it has been for many years.